All right, so we've talked a little bit about what electricity is, the current, the charge. And now we're going to talk a little bit about what we do with that stuff and the math that goes along with it. So we're going to lead into Ohm's law and circuits. And this is kind of the beginning of circuits. You will do some more stuff with circuits in the next lesson. But any kind of circuit is going to have a source for the voltage, and it'll be battery, power supply, plug in the wall kind of thing. Conductors, and those are the wires, connectors, the metal bits that the current travels through. And it's the load, and the load would be a resistor. It's what's doing something. It's the effect of electricity that we see. Light bulbs, radios, televisions, appliances, air conditioners. Those are all big resistors, and they're also called loads. And then some kind of item that controls the electricity. And it can be a switch, it can be a volume control, dimmer switches. Any of those kind of things are going to control on, off, or change the flow. And so when we're talking about circuits, you have to consider we don't just build them, you have to figure out a way to diagram them or draw them. And so there are some circuit elements that you have to have the symbols memorized for. This one's pretty straightforward. This would be the wire, nice straight line. And that's all it is, draw a straight line where a wire would be. And wires aren't always in nice straight lines, so you're just pretending. Like, if I could make it nice and straight, this is what it would look like. And then we have our voltage source or battery. And if we hook up a switch, this is what it looks like. This one is open. And so in general we draw it like that so you can tell the difference between the switch and the wire. You don't have to worry about the motor. You do need to worry with resistors. And so we generally use this top one, the zigzag, for resistors. This item right here is an ammeter, and it measures current. And this below it is the voltmeter, and it measures voltage. And we'll talk a little bit about both of those in a second. But both of those are part of the circuits that we will be working with. You've got to know what these are, you've got to be able to draw them, you've got to be able to recognize them. And so here's a real simple circuit. It's got the parts that we need. It has the battery, it has a switch, we can turn it on and off, and here's our resistor. And it really doesn't matter what that is. That could be a light bulb, or a radio, or just a piece of ceramic that's a resistor to control something. It doesn't really matter, and they're all going to look like that zigzag, not a separate thing for each one. Now, one of the things we need to talk about is resistance, and we've talked about current a little bit, we've talked a little bit about voltage, and resistance is something that works against the flow of current. And if you think about how the hallways are, a highly resistive hallway is that hallway you're trying to go the wrong way in right as the bell rings and everybody's coming towards you, and you end up going in all sorts of directions, and it's really, really difficult to get all the way down the hall. And if it's not resistive, it's empty, it's in between classes, and there's nothing going on, and you just walk straight down the hallway, and that would be very low resistance. And so when the electrons are moving around in the wire, if there's not a lot of collisions, there's low resistance. If it's colliding and getting stuck and having to go in different directions, then it's highly resistive. And so when we talk about this, we measure it in something called ohms, and we use an omega symbol for that. And there's a couple different things that it depends on. Absolutely depends on the material. Because we've talked a little bit about metals being able to conduct electricity. That means that they're low resistance. And when you're talking about metals and wires and things, you also have to talk about how they're shaped. And you can imagine that if it's a really, really long wire, there's a lot of opportunities to collide with things. And so the longer it gets, the greater the resistance. And also, if it's really, really small in cross-sectional area, so if it's a really thin wire, then the resistance goes up also because it's going to be colliding more often. In order to find resistance, there is a meter that'll do that, but we, for our labs, will be using two different meters. You'll have a voltmeter and an ammeter. These are analog, and you may see these, or you may get digital ones. It depends on your setup, but they do the same thing whether they're digital or analog. This top one is the voltmeter, and this one is the ammeter. And once we get those measurements, we're going to use them to calculate the resistance. And so here's a little bit about ammeters. Ammeters measure current, and our symbol for current is an I, and the units for current are either going to be amps or milliamps, and we'll use amps most of the time, and if you get milliamps you have to convert. And so this is 10 to the negative 3 amps. They have a really, really low resistance, and so they're connected in the same wire as everything else. So they measure the current at this spot right here. So wherever it is, it's telling you how much charge is flowing through every second at that spot. And voltmeters are hooked up a little bit different. They have a very high resistance, and they're hooked up what we call across. So it starts at one side of what we're trying to measure and goes to the other side, and it really measures the change in voltage from this point to this point, or what we call the voltage drop. So you're measuring how much voltage is used up in that part of a circuit. And we call this type of a hookup parallel. It has its very own loop, and it's really important that you hook it up correctly. You can actually ruin the piece of equipment if it's not hooked up correctly. And so when a guy named Georg Ohm set up the circuit, what he noticed is oftentimes, so he discovered that voltage, if you measure the voltage, measure the current, and graph it, what you end up with is a nice direct relationship. And so and if you remember your slope equation, the slope of this line gives you the resistance of the circuit. It doesn't work in every circuit, but the ones that we'll deal with that are called ohmic circuits, this is what it is. And so resistance, there's the symbol, and it's measured in ohms. Current is a capital I, and we measure it in amps. Voltage is a V, and we measure it in volts. And you're going to want to, our meters will have millivolts and milliamps, so you are going to have to watch for conversions when we're doing labs. So it has a couple example problems. I think you'll find this math to be nice and straightforward. Nice relief after that Coulomb's law stuff. But we have a current of 3 amps, and we have a voltage of 15 volts. And the question is, what's the resistance? And so Ohm's law is voltage divided by current, and so we take those 15 volts and divide it by 3 amps, and we end up with 5 ohms. The trick will be you'll have to find different parts of this equation, so you may want to either memorize or be able to rearrange Ohm's law. And so one of the other things we have to talk a little bit about is power. And so P is the symbol for power. And it's, if you remember, it's measured in watts, which is also a joule per second. And we still have voltage in volt and current in amps. And then if you recall energy, same energy that we've used before, guess what? Measured in joules. Power in watts, time in seconds. So those are the units you'll be dealing with for those particular symbols. Energy is power times time, and power is voltage times current. Once again, really straightforward math. And so anytime you see watts, it's power. And you'll have to watch for that. It's kind of a hidden information thing. Nobody ever says my light bulb has a power of 100 watts. They say, go get me a 100-watt light bulb. And then the other issue is we like to deal in minutes in real life, but for calculations, we need seconds. So you're going to have to convert it to seconds. So this 100-watt light bulb, energy is what we're trying to find out. Energy is power times time. And so that 100-watt light bulb runs for 600 seconds. And so we get a whole lot of joules. 60,000 joules. Lots of energy. Another power problem. So once again, nobody told you that was power, but it is power. And nobody told you this was voltage, but it's voltage. So we don't use a voltage source of, we just talk about it in its unit sense. So power is 100 watts, and the voltage is 120 volts, and then we want to know how much current does that device use. So power is current times voltage. So to get the current by itself, divide both sides by the voltage, and then plug in your 100 watts, 120 volts, and so when you do the division, you're going to end up with 0.83 amps. And the units are weird. If you're following the units around, watts per volt, you may just have to remember that current is measured in amps. Alright, so this is a bunch of easy-ish math. The hardest part's going to be rearranging the equation, plugging things in the right place. The other thing that you're going to have a little bit of trouble with sometimes is identifying what's what. Remember, watts are power, volts are voltage, and amps are current. So good luck with the start of circuits. I hope you find this very interesting. Bye-bye.